Okay. Hello, everyone. It's very nice to have you all for the second talk of the session. And we're very happy to have Kristan Jensen from Victoria, who's giving us a super early talk about Larsen fractons. So please, Kristan, go ahead.
All right. Well, thank you very much for the invitation to speak. Thank you for the community service that you all have done in the season of plague, giving us such lovely talks the last 2.5 years. I'm happy to do my part. So this is a talk, how to say, so the title is Large N Fractons. Maybe a better title would be Large N, models with exotic symmetry. As you'll see as the talk goes on. Let me zoom back out. So this talk is primarily based on a paper that appeared on Archive in May with a student, Amir Raz from UT Austin. He's fantastic. Don't say that lightly. It's conventional to, prop up your junior collaborators when you give talks, but this time, really, I mean it. He's fantastic. I had another paper on sort of related subjects just under a year ago with Akash Jain, which will not be very relevant for the talk, but is of some other interest. So let's get into it. What are fractons? These are systems that challenge long-held beliefs in our field, dating back to Wilson, sort of fundamental dogmas in quantum field theory concerning the simplicity and the universality of low energy effective field theory. So I'll explain why. But the other comment about these things for the moment is that these are interesting, but at this time, purely hypothetical phases of quantum matter. They have not been discovered in nature yet. It'd be great to find them. But they seem difficult to reconcile with the quantum field theory description in a continuum limit. Let me remind you of the usual things that are true for many systems, many lattice systems, or many, what usually happens, you take your favorite complicated system of interest, like lattice QCD or a string compactification, what have you. It's very complicated. It has many degrees of freedom. It's difficult to organize, but physics simplifies in the infrared, where only a finite number of degrees of freedom are relevant, and we can write down an effective field theory description where all of the microscopic details, how many fields you have, how many Kähler moduli do you have, and so on, gets absorbed into a set of low energy constants, the coupling constants for those relevant degrees of freedom, consistent with symmetries of the problem. And there's, a series of irrelevant operators whose scaling you understand and which decouple appropriately from infrared physics. That's what usually happens. Here is a system that has fractons that seems to defy this entire paradigm. It's called X cube. It's sort of a 3D version of toric code, if you know what toric code is. If you don't worry. I'm going to say what the model is now. It's a spin system on a cubic lattice in 3 dimensions, where spins live on links instead of at vertices. And the basic building blocks of the Hamiltonian are so-called cubes and crosses. What is a cube? Well, what you do is you take a cube in the lattice and you multiply all the sigma x's across all the links of the cube. Call that AC, C for cube. The other building block is a cross. What is that? Well, you take a vertex and then split off one direction from the rest, in this case, Z. So consider the XY plane coming into some vertex, and you multiply all the sigma Zs. I'm in Canada now, so it's sigma Z, not sigma Z, but you multiply all the sigma Zs coming into that vertex. And then, of course, you have different crosses depending on which direction do you take, X, Y, Z. and which vertex you consider. Hamiltonian of this model is a sum of A's on each cube with some coefficient, called alpha, plus sum of crosses in each direction at each vertex with some other coupling constant. And the thing is that this Hamiltonian, although I didn't say it, the reason why these guys considered it is because it's a sum of commuting projectors. So each of these A's commutes with A at each other site. That's sigma x's always commute with sigma x's, but they also commute with the B's at every site. So to solve this Hamiltonian, if you were in an undergraduate quantum mechanics class, what would you do? Well, you would simultaneously diagonalize all the A's and B's. In particular, the ground states, if alpha and beta are positive, would be given by, all those states, these A's and B's, they square to 1. And so the ground states are those states that satisfy A equals -1, B equals -1 everywhere. The thing is that that is actually a very strong constraint on the spectrum. And when you solve it, you find a number of exotic features. So feature number 1, the number of states that satisfy that condition that I just said, A equals B equals -1, the ground states. Well, there's a degeneracy of them. There's many of them, and that degeneracy is UV sensitive. We're used to, in condensed matter systems, there sometimes being a non-trivial ground state degeneracy. This happens in, for instance, the quantum Hall effect, where if you place a quantum Hall droplet on a torus, say, or a space of non-trivial topology, some surface of genus G, there can be a degeneracy that depends on the genus. You can think of as coming from, in a Chern-Simons description, the various Wilson lines you can place around the cycles of this higher genus surface. Well, here you have a ground state degeneracy, but it's not coming from topology. It's sensitive to the number of lattice sites. In particular, that degeneracy goes like in a fine lattice limit. It goes like 4 to the number of planes in the lattice. The exact number is what I wrote here: 2 to the number of lattice sites in the x direction, plus 2 times number of sites in the y direction, plus 2 times number of sites in the z direction. And then there's the fun factor of -3 that you can work harder to figure out. This leads to a 0 temperature entropy that is, well, it's not extensive, doesn't go like the volume of the system. It's sub-extensive, but it's still quite large, going like the number of lattice sites parametrically in a given direction. So that's one feature about this thing that's very odd. There is a UV sensitive spectrum of low energy states. Second thing that's strange is that there are finite energy excitations of restricted mobility. This model has so-called fractons, which are excitations that are stuck at a link and can't move. It has line-ons. These are excitations that can only move along a line of the lattice, can't move in the transverse directions. And it has plane-ons. These are things that can move in, well, a plane and not in the transverse direction. That's all. Last thing that's strange about this system, it was written down as a commuting projector Hamiltonian. But it has a very large symmetry. It has an unconventional symmetry, sometimes called subsystem symmetry. Ordinary spin models at 0 applied field, we're used to them having a Z2 symmetry, where you flip the spins at all lattice sites simultaneously, right? Well, this model has something much larger. So what you can do is you can take, imagine fixing a plane of the lattice, take all the spins on that plane and flip them while leaving everything else alone. That is the symmetry of this Hamiltonian. kind of like gauge symmetry in the sense that it's a local symmetry. It's not a gauge symmetry, it's the wrong way of thinking about it, but it's a symmetry that acts much more locally on degrees of freedom than we're used to. And in fact, these other pieces of exotic physics, the ground state degeneracy, the restricted mobility excitations, those are both really traced back to this third funny thing, the subsystem symmetry. So for instance, in this model, the subsystem symmetry is spontaneously broken. If you pick a ground state, it transforms non-trivially under subsystem. And if you act with subsystem on like a seed state, you can map out all the different ground states. And because the symmetry really depends on how many planes you have in the lattice, it's a UV sensitive symmetry whose volume, roughly speaking, the volume of the subsystem symmetry goes like this ground state degeneracy. And the restricted mobility excitations really arise as a consequence of conservation laws associated, word identities associated with this funny symmetry. And the question is, at some level, can quantum field theory or some suitable enhancement thereof, something that's maybe a little bit different from the textbook procedure, can it describe systems like this? And again, to recap the features that are really challenging that we have to be on the lookout for are this non-topological lattice-sensitive spectrum of low energy states, this ground state degeneracy, and these restricted mobility excitations. But maybe another way of packaging all this at once, we want a careful quantum field theory-esque treatment of systems with these exotic symmetries, like the subsystem symmetry. And I say QFT-esque to sweep under the details, all the concerns, is what we're about to do quantum field theory or not. So today I'm going to showcase a class of models where the answer is basically yes, if you're willing to be a little bit more flexible with your definition of what quantum field theory is. And the kind of thread that we're going to follow is this thing that, all this funny physics is really a consequence of these exotic symmetries. And at least as high energy theorists, we know how to implement symmetry in a systematic way. So for this talk, we're going to fix a lot of symmetry. That's what we usually do. You start with more symmetry, even it's n equals 4, and you slowly reduce the amount of symmetry. Start with the most and then work back. So the kind of models I'm going to consider today are models that have a translation symmetry. There's a time translation generated by a Hamiltonian. There's going to be spatial translations generated by momenta. It's rotations. There's a U1 charge. And instead of a subsystem symmetry, my exotic symmetry that I'm going to enforce is a conserved dipole moment. The usual freshman physics thing, charge times vector, position vector. At least that's, okay, for technical reasons that I won't get into, that's the right definition to consider if you're in infinite volume. Finite volume, I have to think a little more carefully what's going on. So in this context, what's the relation to what I said before? Well, by conservation laws, by these symmetries rather, if you have an isolated charge, it can't move. Because if it did move, that would change the dipole moment. That's the idea. And what we want to do now is we want to write down an effective field theory of some charge degrees of freedom invariant under these symmetries. Fortunately, well, at least for complex scalar phi being the charge degree of freedom, this problem was basically solved by Pretko when he was a postdoc at Boulder back in 2018. So let's take an ordinary complex scalar phi. It transforms under U1 in the usual way by a phase rotation. A dipole transformation, the one that would lead to conserved dipole moment like this corresponds to a transformation d dot x. So that's that. And well, because that phase rotation depends on position, you know, one consequence of this is that in your algebra of charges, you'll have a non-trivial commutator between translations and dipole. Okay, so let's try to write down an action that is invariant under these symmetries. Well, translations and rotations, those are easy enough to take care of. U1 is easy enough to take care of. We just have as many phi's as phi bars. What about the dipole moment? Well, in the absence of Lorentz symmetry, so that we can write down things with like a single time derivative, the lowest derivative operators that you would start writing down in a Lagrangian are things like, you know, phi bar dt phi. You have a potential term. You might try to write down a standard like spatial kinetic term, grad phi squared. That ends up being inconsistent with this dipole symmetry. It breaks it. So that this symmetry kills those terms. And in fact, the simplest terms that you can write down that have spatial derivatives are unconventional. We're not used to them. They're non-standard. That's what I'm writing with this funny dij. So what is this dij? This dij is a bilinear, has two derivatives, two powers of the field. It's the natural, it's sort of an object that under dipole transformation is covariant. So like an ordinary one derivative term, there's no way to make it covariant under dipole transformations, but with two fields and two derivatives, you're in business. So the simplest kind of term that you can write down then is one that has, well, basically trace of that guy, and then two anti-scalars. It's quartic in the fields, has two derivatives. There's other terms that you can write down that have a similar structure, four fields, two derivatives, four fields, four derivatives, and so on into the sky. You can write down as arbitrarily complicated terms as you want. But this is kind of enough to highlight an important lesson, which is that, you know, there's not going to be a free field model other than a very singular one where there's no spatial derivatives at all that has this dipole symmetry. And you can just kill all the derivatives. That's like saying you have completely decorrelated degrees of freedom at each lattice site, if you will. That's not something of interest to us. We want to have the dipole symmetry and for degrees of freedom charges at different points in space to be able to talk to each other. But the problem is they can only do that through interactions. And then the question is, well, what do we do? So that's the question marks. What do we do? So option one, we can imagine doing, you know, it works better if you're in person. Can you see the fingers twisted here? So you can do this and hope for the best, basically. Say, oh, well, maybe these interactions, these quartic terms, maybe they're small. Let's try to hope that they're small, maybe, and treat them as a perturbation and see what happens. So in other words, expand around a quadratic Lagrangian where you have a single time derivative term and like a potential, quadratic potential, treat everything else as small and see what happens. Now, something that if you do that, you're going to get very confused very quickly because, you know, imagine like a one loop correction to the propagator. And what's the one loop self energy? Well, in this model, there's quartic interactions, so those will lead to bubbles. There's no cubic vertices. There'll be a bubble and with a momentum dependent vertex that you hope is small. But the thing is that the momentum, the only momentum dependence there is through the vertex. The free propagator doesn't depend on K at all. And so that integral, roughly speaking, goes like k to some power, you integrate over all k, and that's at least, that's a tricky integral to deal with. In dimensional regularization, integrals of that type are just, that's 0 by Veltman's formula, which would suggest that all these loop corrections simply vanish. Is that true? Is that too fast? It's unclear. Okay, here's another thing you might do. Something you might do is to take your potential to be quartic, the Mexican hat thing, with a minimum at not zero field, so that you can try to force symmetry breaking. So you try to force symmetry breaking, you can imagine doing that by tuning the potential to be very deep. And at some level, this is also this kind of an approach where you twist your fingers and you hope for the best. Because, this is classical physics. It's unclear if the quantum corrections strongly renormalize this potential, if the radiative corrections are small. But, if they are, so you try to condense the scalar, and then it turns out that the Goldstone field that you would get, the phase field that you get, well, if you ask how do these various symmetries, the U1 and the dipole, how would they act on it? Well, U1 would act as a phase shift, usual way. Dipole would act as a linear shift by vector, by d dot x. And is there a quadratic effective theory and variant under these symmetries that you can write down for the Goldstone field? Yes, there is. Just instead of having grad chi squared, you would have grad squared chi squared. So a higher derivative Lagrangian, in other words. Sometimes, so a theory like this, back in the older applied ADS CFT days, you might have said this was a Lagrangian that had a Lifshitz symmetry with Z equals 2. That approach is interesting. If you will, you should think that it describes maybe a part of the phase diagram of models like this under the assumption that radiative corrections can be neglected, or at least that they're small. Today we're going to do something complementary to both of these. As a particle theorist, I'm going to bring large N into the game, where we have many results dating back to the 70s that we can kind of, well, we can't use them, but we can generalize the spirit of those results to be able to figure out what happens in this model. What are the what's the phase diagram of models like this? So what's the idea? Before I was writing down models with the U1 symmetry. Well, I'm going to make phi an n component vector. There's n of them now. I'll label it by an index. So there's a phi A, with A going from 1 up to n. And I'm going to, in order to have a nice large n limit, I'm going to impose even more symmetry than I did before. I'm going to impose a UN global symmetry that rotates, these n components into each other. And that UN, well, it has an SUN part and a U1 part roughly. The SUN part, I'm going to impose as an ordinary symmetry. And for the U1, that's where my dipole symmetry is going to be. So in other words, I impose the full UN symmetry, and then I impose the dipole symmetry associated with the U1, the center of the UN. All right, let's write down a Lagrangian. Well, that's what I did here. This is like the simplest possible thing that you can write down that has a nice large n limit. I switched from real time to imaginary time. So I want to do finite temperature physics and zero temperature physics. I have a phi A, so my one time derivative term becomes phi bar dt phi with flavor indices contracted. My funny two derivative 4 field. Now, well, there's some kind of flavor index contractions to deal with. Fine. I introduce a factor of 1 over n in that quartic interaction in the usual way, so that this whole Lagrangian is order n. And now what do we do? Well, we kind of do the usual thing. Let's take n to be very big and try to solve the model. Now, 50 years ago, of course, physicists studied models that were not like this, but they were, schematically similar. They had a large number of fields, but no gauge interactions. So think like, phi being a vector and, grad phi squared and some potential. And the way you would have solved this back in the day was by a Hubbard-Stratonovich. This is the fancy way of saying you integrate in a scalar field sigma that on shell is phi squared. And you can write down a new theory where you decouple the quartic interactions. You have a field sigma squared. No, sorry, a field sigma with an action sigma squared. And then instead of having a quartic term, you have a cubic term for sigma phi squared. You integrate out sigma. That's a Gaussian integral. It sets sigma basically to phi squared. You plug that back in, and now you get an action that goes like phi to the 4. But phi appears quadratically in this action, so you can integrate it out, and you get a simple effective action for sigma with a log det coming from the one determinant for phi, and then you have to still take care of the interaction. The nice thing is that effective action for sigma, for the degree of freedom that you keep, there's a factor of n in front because you have n fields. And so roughly speaking, 1 over n is h bar. It's small. This is a weakly coupled theory. And classical, the classical equation for motion for sigma gives an excellent approximation to things like the free energy of the system allows you to find the phase diagram and so on. And then all of the 1 over n corrections, they're really quantum corrections in this theory. So you develop a new effective description in terms of sigma that's weakly coupled at large n. That's the old story. Here, that completely fails because, I scrolled down too quickly. The quartic term that we have to deal with, this guy right here, that is showing up on the screen now. Okay, so that thing is momentum dependent, and it's not the square of something. So we can't decouple it by integrating in a local degree of freedom that's like phi squared. You have to do something more clever than that. Fortunately, there's a way to do this. It's the way that people solved Chern-Simons matter theories at large n in the early 2000s. It's the way people solve SYK. Something you could call a generalized Hubbard-Stratonovich. Yes, anything is, once you allow yourself to use generalized, it gives you a lot more freedom in what you mean. This is this G sigma thing that you might have heard about over the years. What is it? Well, you integrate in bilocal degrees of freedom instead of local ones. So instead of a sigma of x, you integrate in a G that depends on 2 points, x1, x2. Instead of being phi squared on shell, it's phi bar at 1, phi at 2. I mean, if they were the same, then that would be a local field, but you allow yourself to have them at different sites. And the reason why we call it G is because its expectation value is the propagator for phi. That's the Green's function effectively. And then when we integrate that in, we need a Lagrange multiplier that sets G equal to phi bar phi on shell, and we call that Lagrange multiplier sigma. Well, I'll spare you the details, but if you do that, then you can rewrite the quartic interaction up here basically as G squared, in which case the phi appears quadratically. You integrate it out, and now you get an effective action for G sigma, a collective field action. And the form of this action is, well, there's a log det, like there was before in the old Hubbard-Stratonovich, except now there's a self-energy that appears inside there. The quartic interaction becomes, well, what I've written here, it's easiest to write things out in momentum space. There's some quartic interaction that's like a G squared term in the effective action. There is a sigma G coupling that's a relic from when sigma set G equal to phi bar phi. And then there's the quadratic term in the action, phi squared times chemical potential, which becomes, well, it's just phi bar phi, so it becomes a G. And this quartic interaction in momentum space, this is the includes the contact interaction as well as this funny momentum dependent thing that enforces the dipole symmetry. What is it? Well, it looks like this right here. Lambda 4 is the ordinary like contact quartic interaction, and this lambda, well, this is the funny new dipole invariant coupling. So if you will, you could write this as some quartic vertex this way with Feynman rules and so on. And this effective theory for G sigma, this is just like in the old Hubbard-Stratonovich story, this theory is weakly coupled at large n. G sigma are the weakly coupled. You know, whenever you have a large n theory, it's effectively classical in some variables, right? This is something we've known from the 80s. So the task is, in some level, is to find what are the weakly coupled degrees of freedom? What's the good semi-classical effective description? For n equals 4 at strong coupling, it's type 2b string theory and ADS 5 times S5. Here, G sigma are the right weakly coupled degrees of freedom that organize the physics of the model. And so what do you do from here? Well, those are the weakly coupled degrees of freedom. They have equations of motion. You got to solve them. That's going to give you the leading approximation at large n, analogous to, you know, solving for the gravitational background in holography. So what do? So we need some way of kind of simplifying the problem. What we do is we make, because these G and the sigma, they're bilocal degrees of freedom. And in general, it's kind of hard to solve equations of motion for things that depend on two positions. So what do? Well, we use the symmetries. We assert that, or perhaps we make an ansatz that G and sigma are translationally invariant. In other words, that their dependence on the two momenta, they really only depend on one, and the dependence on the other one is fixed by momentum conservation. So what's left is a G of K and a sigma of K. And what you find when you do that is that the equations of motion for that G sigma, they read like this. G ends up being 1 over I omega plus sigma. That looks like a free propagator I omega, or 1 over I omega, dressed by a self-energy, sigma of K. That's not it. There's another equation that relates sigma back to G and gives you a closed set of equations. That one reads sigma of K is, well, this quadratic term in the potential, which you could identify as chemical potential, so minus chemical potential, plus an integral over another momentum, K prime, G of K prime, and then a certain limit of the quartic interaction. But if you stare at this for a little bit, you realize that what this equation is, this can be represented more simply diagrammatically. What this is saying is that the self-energy is minus mu plus a bubble, like a one-loop diagram, where the thing that runs around the diagram is the leading large n propagator G. And there's a quartic vertex, which is this D4. that funny structure of momenta corresponds to, well, you have momentum k flowing past the vertex and a k prime running around the loop. And then you just amputate the external legs. Well, long story short, these equations can be solved. If you want to solve equations like this, there's always a trick. There's always, some things that help you. In this case, for those that ever want to be able to do these kind of things themselves, say in other contexts, if you want to solve equations like this, how even do you begin? The important thing is to note in the equation for the self-energy, the left-hand side is a function of like an omega and k. How does the right-hand side depend on omega k? And the answer is because of, the propagator running around the loop depends on an internal momentum. The only dependence on external momentum is through the vertex. And in this case, the vertex is a polynomial in k and it's frequency independent. That's enough to tell you that the self-energy, it's frequency independent, and it's a polynomial in k. And what you can do then is you can make an ansatz, most general polynomial in k, that's characterized by a finite number of coefficients, and you get a finite set of equations for those finite coefficients, and at worst, you can solve those numerically. Simplest thing you could do is make a rotationally invariant ansatz, characterized by two constants, call them A1 and A0 coefficient. So in this simplest model, the self-energy, it's not just a polynomial in k, but it's polynomial degree 2 because the quartic interaction is at most k squared. There are two spatial derivatives in the thing I wrote, so you'll get let me bring it back down. So the quartic interaction goes at most as k squared. So you can write down an ansatz for the self-energy that has a k squared piece and a constant. You can find solutions then. And what happens is you get a non-trivial solution. The self-energy is momentum dependent. And this has the practical consequence of attenuating physics at high momentum. The loop integrals that you have to deal with are relatively prosaic then at large K. Furthermore, I guess I should say the constants that you get if you solve them in the regime where this kind of funny dipole invariant quartic coupling is small, you get answers that depend non-analytically on this funny dipole coupling. This is consistent kind of with the things that we were talking about earlier, where, what can you treat these things perturbatively? Well, at large n at least, the solution that you find depends non-analytically on that coupling, and therefore there's not a good perturbation theory at coupling equals 0. You really have to resum an infinite class of, an infinite tower of corrections, which can be done at large n. That's not all. Turns out, well, we didn't find just one solution, we found many solutions. And the reason for that is because of this dipole symmetry that I keep harping on about. So earlier I said, well, the dipole symmetry, it acts as phi of Tx is shifted by a phase d dot x. And if you Fourier transform, what that means is that in Fourier space, phi under a dipole transformation gets shifted from omega k to omega k plus d. And you can see that at the plane wave level. So, in other words, in this effective description of G sigma, how does the dipole symmetry act? Well, it takes the G of K to a G of K plus D. That's the same thing for the self-energy. And so the solution that I described above, where sigma depends on K, and therefore the Green's function, G, also depends on K, well, dipole transformations act on it to generate a whole family of solutions to the large N model. There's, in fact, a solution for every such D, every such dipole transformation. So in other words, what we have found in this model is dipole, the spontaneous breaking of dipole symmetry. So we implemented this funny new symmetry, the dipole symmetry. Lo and behold, it's spontaneously broken in this model. At some level, this makes sense. This Green's function, phi bar phi, well, if the points are separated, this is a good order parameter for the dipole breaking. It's kind of like a dipole condensate. If you think about it, you put charge at 1, anti-charge at 2. It has a dipole moment. Okay, so we find this dipole breaking. And then, you know, the one question that you then have to ask immediately is, well, how many such solutions are there related by the symmetry? That will determine sort of the structure of the Euclidean path integral. In other words, in the imaginary time formalism, the Euclidean partition function is going to go like an e to the minus, you know, on-shell action. That's order n, times a prefactor, a one-loop determinant, which comes from, you know, fluctuations around this large N saddle that we found. But it includes something very special. It includes zero modes, or if you will, a sum over all of these different solutions related by the dipole symmetry. The question is, well, what is that? Now, here's where the fun begins. If you weren't having fun already. So this D vector, notice it's valued in the space of momenta. K to K plus D. So now we have to deal with something that someone could have pushed me on earlier in the talk. No one did. What's the space of momenta? That depends on the kind of problem we're considering. For an infinite volume, the space of momenta is infinite. If we're in finite volume, the momenta are quantized. And if we're in a lattice system, well, there's even more because the momenta live in a Brillouin zone. The same statements hold true for these dipole transformations, D. And in fact, if we have in a lattice regularization, if we have a lattice, and that's sorry, if we start from a lattice version of these models, then these dipole transformations, they live in the Brillouin zone. We're talking about a finite lattice. That volume of the Brillouin zone, well, that's really discrete. There's a finite number of single particle momenta in a finite lattice. In other words, that leads to a finite number of solutions to these large N equations. That's just it's like the dimensionless version of volume of this Brillouin zone, counting how many different lattice momenta you have. And there's as many lattice momenta as there are sites on the lattice. And so the symmetry factor that we need, how many different large N solutions are there? It's really just the number of sites on the lattice. So what we get then at leading order and large N for Euclidean path integral in this model, if we kind of step back a little bit from the continuum limit, we have an e to the minus s naught being the on-shell large N action, it's order N. There's this prefactor arising from the dipole symmetry that's counting how many different large N solutions we have. And then we have, the rest of one loop determinant for fluctuations of G sigma around their large N values. Plus, higher order corrections in 1 over N. Now there's things to be said. The model that we wrote down, whether we wanted it to have it or not, it has UVIR mixing. It, strictly speaking, it's not a complete continuum model. In order to get a finite answer for partition function, one has to do more than just renormalize physics at high energy. There is a physical sensitivity to the lattice that remains in the infrared. And it has to do, maybe a way of saying it is that, well, we have this prefactor going like number of lattice sites. Now, that being said, this UVIR mixing, this is something I warned about earlier in the talk. It's something I said was characteristic of these systems with exotic symmetry. Well, we found it. We didn't have to work that hard, really. And at some level, it's kind of innocuous. Again, a Hamiltonian picture for the partition function where, this is, trace e to the minus beta h. This UVIR mixing, this is a funny thing to consider. This means that there's a lattice sensitive density of states. But from the point of view of Euclidean path integral, at least, this lattice sensitivity, this prefactor, it really just arises through kind of a symmetry factor. We have many solutions, many saddles to the model, and properly counting them requires knowledge of the lattice that underlies the system. And at least in perturbation theory, around any fixed such configuration, that's perfectly fine. You can compute loop diagrams aplenty. In particular, the self-energy gets these momentum-dependent corrections so that you can make sense of a loop expansion. I guess I do want to stress in this model, there really is a it has this feature that you can write down a continuum Lagrangian, but at some point it hits you that this model doesn't have a good continuum limit. Now we've done a lot more in our paper. We studied another phase at large chemical potential. That's the one where the tree level potential in the model becomes Mexican hat type, and you might have symmetry breaking. In D equals 2, you don't, thanks to a version of Coleman-Merman-Wagner appropriate to this. But in D above 2, you can get such U1 symmetry breaking. And so the phase diagram that you end up finding in this model is schematically what I've drawn over here. Roughly speaking, there's 2 phases. There's one at large chemical potential where the tree level potential becomes Mexican hat. The U1 symmetry is broken. That means the dipole symmetry is also spontaneously broken, it turns out. And then there's another phase, which is the one I was talking about above, where the Green's function goes like 1 over I omega plus, let me write it like this, A1 k squared plus A naught. Down here, the Green's function, it goes as 1 over I omega plus A1 k squared, and then there's a condensate associated with the symmetry breaking.
I
so we're
have
able
a
to find
question.
finite temperature. Oh, go ahead.
Yeah, sorry. Yeah. You mentioned the Coleman theorem now in D equal to 2 to say that it is impossible to have U1 symmetry breaking. Is something similar affecting also the spontaneous breaking of the dipole symmetry?
Absolutely, absolutely. Yes. So what happens here, how to say, the right. Okay, so there's Coleman-Merman-Wagner abounding. The Coleman-Merman-Wagner theorem for the dipole symmetry in this context would imply that actually there's no dipole breaking in D equals 2 either. However, there's a question when you're in a large N model, can large N see that? You know, the analog that you may be more familiar with is in holography. You know, you can have holographic superconductors in ADS4 finite temperature, even though that's inconsistent with Coleman-Merman-Wagner. What gives? Well, the restoration of symmetry by infrared fluctuations in that setting is it's a 1/n effect. This is essentially something that was solved by Witten, well, communicated to the masses by Witten in the 80s in a lovely paper on Thirring models in 1+1 dimensions. The idea is that in a large N theory, you can have what's, you can have, how to phrase it? You can have a context where the 2-point function decays with the power of x to the n, which simulates for, or, sorry, is that how it goes? Or x to the 1/n. Which simulates a condensate at distances less than n as you take n to infinity. There's an order of limits issue. What do you take to infinity first? X, the separation, or n? So in this setting, the Coleman-Merman-Wagner, okay, it applies to the dipole too. What's special about, why do I mention it in D equals 2 for the UN, for the U1? Really, it's the UN. When there's U1 breaking here, then UN is broken to UN -1. And in 2+1 dimensions, well, if that was the case, then you would have n, roughly speaking, Goldstone bosons associated with the symmetry breaking. But the infrared fluctuations of those n Goldstone bosons is sufficiently large that it would destroy the putative order even in 2+1 at large n.
Okay, thanks.
Yeah. So one lesson from this is that in this phase diagram, the dipole symmetry is broken everywhere. You get gapless phases everywhere, including, or at least in the, we know for sure that you get gapless phases in the thermodynamic limit anyway. There's a subtlety that I could comment on about finite volume physics if you want for the dipole breaking but U1 preserving phase. In particular, in this phase up here where UN is preserved but the dipole is spontaneously broken up above that line, there's a natural candidate theory of a dipole Goldstone that you can write down that realizes all symmetries of the problem. Except instead of being a scalar Goldstone, it's a vector Goldstone. You can call it psi vector. Under dipole transformations, it just shifts, kind of like how an ordinary Goldstone boson shifts under U1 transformations. And in fact, you can write down a candidate quadratic theory of such a dipole Goldstone quite simply. It's just derivatively coupled. So for instance, you could have psi vector dot squared minus terms then with spatial derivatives. So, you know, divergence of psi squared minus psi dot grad squared psi plus da da da. So this model, you know, you have to work hard to find these phases, but once you do, we expect there to be a very simple low energy Goldstone-like description of all these phases. The U1 broken phase with a scalar Goldstone, that one you can kind of make a guess from the classical action that you write down, what it is. It's going to be this Lifshitz-like thing that I wrote before. This other phase where dipole is broken, but U1 is not, well, we wouldn't have known about that phase if it wasn't for solving the model. But once we know that it's there, there's a simple candidate Lagrangian, effective Lagrangian that you can write down. We've done a lot more too. We've studied models that have subsystem symmetry instead of U1 symmetry. I guess I'll comment at the end about sort of future directions that we're pursuing. There's a lot of them. It's kind of like a laboratory for investigations. You know, the advantage of the models I've written down here is that, you know, that I guess it's kind of implicit in everything I've said. These models of fractons, they're usually commuting projector Hamiltonians, completely integrable systems. Or, you know, you take kind of extreme limits where you have Goldstone Lagrangians. But, you know, to have soluble interacting models with these symmetries, that's the contribution that we've added to this literature. As far as I know, there's nothing else really on the market. Now, last comment, and then I'm done basically. One surprise about this model, you could ask at the very end, we have these gapless phases, we have UV sensitivity, but you have mobile excitation, so you can ask, where are the fractons? Doesn't seem to have them. One way of saying what's happened here is we wrote down a Lagrangian whose microscopic degrees of freedom are immobile fractons, these elementary charges that can't move by symmetry. But what's happened, as in retrospect, what usually happens in quantum field theory is that the microscopic picture is not the physical one. Interactions dress those elementary charges in such a way that they become mobile quasiparticles. In the U1 broken phase, they're genuinely gapless. There's a condensate and they can swim in the sea. But in the dipole breaking phase, well, I mean, look at the Green's function. That describes a mobile excitation, a charged excitation that's mobile with some dispersion relation, omega going like k squared. So even in the dipole breaking phase, elementary charges become mobile thanks to interactions. So we tried, this is what happened. However, I should say, one can get models that genuinely have fractons by coupling the model I wrote down to a sort of generalized notion of electromagnetism suitable for systems with dipole symmetry. Where at times, that's a discussion I can't get into right now, but suffice it to say that everything I've done, it's kind of the proper treatment of these interacting models so that you can have a launching pad to do all sorts of other things. You can find models with fractons, you can study renormalization, you can study systems with subsystem symmetry, all this other kind of stuff, much of which we're doing in progress. It would be, at the moment, it'd be great if other people do too. So with that, I'll say, thank you very much for your attention.
Thank you, Kristan. Very nice. Let's see if we have questions. We should. Please don't be shy.
Hello.
Hello.
Somebody else is asking?
Yes, I have a question, Kristan,
Yeah.
if I can ask.
Go ahead.
I think if you could go back to the point where you mentioned UV-IR mixing and the partition function has a dependence on the number of lattice sites, something like, yes, excellent, yeah, right here. So you say, I just want to make sure I understand. So when you say that the dependence or this UV-IR mixing business is innocuous, is it because you're observing that the basic dependence of the partition function on the site, or sorry, on the lattice is just through the number of sites by this n sites?
That's what I'm trying to say. Yeah. It's not the only. There's always a question when you give a talk, how much do you say? This is not the only sensitivity to a lattice.
Good.
How to say, when it comes to finding the how many large n solutions are related by symmetry, this is the sensitivity to the lattice that is there. Now, there's another sensitivity, though, that, well, there's two other things that you can worry about. They both happen. They're not quite as eye-popping as this, if this is actually eye-popping. The first is that, how to say, there can be excitations or other configurations, other fluctuations that you have to sum over.
Yes.
That, roughly speaking, it's easiest if we pass to this Goldstone description to explain what these things are. So I claim that there's a Goldstone-like description of this model at low energies, where there is a dipole Goldstone that shifts under dipole transformations.
Mm-hmm.
And what can happen is that, I mean, you should ask whenever you have a Goldstone, is it compact? Is it non-compact? If it's compact, then in finite volume, you can have configurations where the Goldstone winds in field space as you go around a physical circle. And indeed, I mean, those, okay, if you're talking about finite volume physics with a finite lattice spacing, that happens. The psi and the d vector in that case is quantized, it's compact. And you can have configurations where the psi winds around a spatial circle. Those corrections, those lead to additional terms in this one loop determinant. So the subleading at large n, they're still there. And you really need to carefully work at, like, almost lattice spacing is almost zero to resolve the extra states in the spectrum associated with those winding modes. That's one thing that can happen. The other thing that can happen is that you can consider operators in this theory that are charged under dipole and look at their correlation functions. And when you do that, those operators, those can exchange, if you will, the zero modes associated with the symmetry breaking. And so those correlation functions, those have a lattice sensitivity that has to be carefully treated. From the point of view of the Goldstone description, if you talk about something like psi I, psi j, well, that's where you would have to be very careful.
Yeah.
Most operators that you deal with, though, especially in the low energy limit, are dipole invariant, things like the stress tensor or the currents of the model. And those, so, if you deal with di psi j d psi roughly, then those zero modes cannot be exchanged. And those have a very nice behavior in the continuum limit. There's no lattice sensitivity that remains. And even this like prefactor drops out because, this is coming from derivatives of log z.
Okay, thanks.
Yeah, no, thank you.
Any other question?
Yeah, I have another question. You mentioned the Hubbard-Statonovich duality, but then you seem not to be confined to 2+1 dimension in your effective field theory. Is it?
That's right. I mean, the old Hubbard-Statonovich story, you could do in any dimension.
Okay. Yeah. Is it just technically more difficult, or?
No, I mean, if
because I'm thinking to particle vortex duality, like as a proxy for Hubbard.
So if we open to the chapter in Zin-Justine,
okay,
on the old vector models, it's done in any dimension.
Okay.
You can just do it. You can do it all at once.
Okay, I see. Then I have another question, which is probably naive. When you mentioned the Goldstone vector, is it anything similar to like a phonon? Like it seems like a collection of Goldstones, or well, in that case, translation breaking. I don't know if the effective field theory look alike one another.
Yeah. It does reset. Yeah. So Okay, so in a proper treatment of phonons, theory of solids, the relevant degrees of freedom are displacements of the constituents of the lattice from their equilibrium positions. UA vector, right? The thing is that, well, how to say, if you consider like a Fourier space version of that displacement, so that everything's moving in concert, that description has a redundancy. You translate everything by a single lattice spacing, you're back to where you started. So if you talk about collective behavior of the coarse-grained U really is subject to some redundancies. It lives in the single cell, right, of the lattice. So in other words, U lives in like the conjugate of the Brillouin zone. And then translation symmetry would imply it's derivatively coupled. So said this way, yes, this dipole breaking phase, it's like a conjugate almost of phonons, where the redundancies are the reciprocal ones. Instead of living within a unit cell of the lattice, this dipole gold zone lives within the Brillouin zone, its conjugate. The dual lattice.
Okay, thanks.
Yeah.
Any other question? Or more questions? Comments?
Oh, can I ask a question?
Navid,
Daniel?
go
Hi, Kristan. Thanks a lot for the interesting talk. My question is about your statement about the non-analyticity in the structure of G. I think if I have understood correctly, you mentioned that you see some sort of non-analyticity in terms of coupling constants. Is it true? Did I?
Yeah, that's right.
Yeah, but okay. My question is, you start with some perturbative framework. I mean, in this framework, we expect to find some results perturbatively in terms of coupling constants before any resummation, for example. Then why do you see some sort of this? Yeah.
Oh, so the statement is that a naive perturbation theory is it's not able to find this this phase that we found at large N. So what we can do is we can resum at large N, and then take a small coupling constant limit to see how the physical solution behaves.
I see.
And what we find is that behavior is non-analytic at around coupling equals 0.
So
and
you
so
arrive at
the way that I think about this kind of tells me ex post facto why I shouldn't have done this perturbation theory in the first place.
Okay, thank you. Thank you.
Yeah, I have another question. The interactions that makes the fracton propagate, do they depend on n? I probably missed the point. How is it related to the large n limit and the interaction?
Yeah. Sorry, there was a lot in this talk. So the Lagrangian that we started from, I mean, that's the simplest possible thing that we could do was this right here. And the interactions are this, and then an ordinary quartic interaction. You can do more complicated things, but this is just what I presented because you present the simplest thing. And in this case, there is n dependence, but the n dependence is introduced so as to have a nice large n limit. What we want is for the action to be of order n. That's the usual thing. If you were in a gauge theory, you would want it to be of order n squared. Here we don't have the gauge degrees of freedom. We have n flavor degrees of freedom. So we want the action to scale as large n. Well, there's a single sum over n. So the one-time derivative term is order n. And then these quartic terms, we introduce a factor of 1 over n out front so that when we have, the two flavor contractions, those each give us a power of n, and then we have a 1 over n to compensate. This is like what one does in SYK or Chern-Simons matter theory or all the usual things.
Yeah, okay. Thanks.
Yeah.
Well, we've had a lot of questions, but let's see.
I have another question, if I could ask it. Sorry, squeeze it in.
The speaker is facing.
Kristan, could you go to where is a point where you wrote down like what the action looks like in the symmetry breaking phase? If you expanded around condensate. You're supposed to get some sort of Lifshitz theory, right? Some z equals 2 Lifshitz theory. Excellent. Yeah. How does mu show up here by any chance? You wrote down the kinetic term. Is it also like mu squared chi squared or something like this?
So the way that the dipole symmetry in the U1 is realized in this theory is through this.
Yeah. Okay.
And so that symmetry is sacrosanct. The chemical potential in the original Lagrangian preserves it. And so however mu appears in the low energy description, it'll be consistent with the symmetry with chi transforming this way. So chi squared would violate both U1 and dipole.
Yeah.
So you can't have a chi-squared coupling. You can have, what, sorry?
It would be derivatively coupled or something.
Yeah, you can have a derivative coupling, but you can have more. Mu can just appear, I mean, you should think of mu as a microscopic parameter. And then all, as a result, low energy constants can all depend on mu. So all the couplings in front of these terms can also depend on mu.
I see. And would it be possible at that point to, if I take this theory, then I think in this theory, I can do like basic dimensional analysis now, because I have a proper kinetic term. And then I can work out, at least in this phase, like what the dimension of, say, mu is. And then would I then get like, if you go down to the phase diagram that you wrote down as a function of t and mu, or t and mu squared, I can't remember exactly which variables it was.
Yeah, t and mu is what I had there.
T and mu, exactly. Would that be, do you happen to know if I would then be able to predict the shape of this curve just by dimensional analysis, at least leading order, what the shape of this curve looks like? At least it might make sense in the U1, at least on the side where U1 is broken.
Yeah, we don't have an analytic form of this. The complication is that, say, this kind of quartic kinetic term in the original Lagrangian had that coupling constant persists. It doesn't decouple from the infrared.
Okay.
And so, and it has non-trivial dimension. So kind of like a naive dimensional analysis where you just keep t and mu and nothing else is insufficient, at least in this model.
I see. Okay. Great. Thanks.
You can compute the low temperature large n solution. in this U1 breaking phase.
Mhm.
And you can see how the parameters depend on the various constants in the problem.
Mhm.
At exactly 0 temperature, this quartic coupling isn't there.
Okay.
But at any finite temperature, which is relevant for the thing that you're asking, finite temperature corrections, you can think of it almost as like Boltzmann kind of, the Boltzmann suppression is not enough to completely get rid of those higher derivative couplings.
Mhm.
Well, higher dimension couplings, not higher derivative.
Okay, but you can answer, then you can therefore then analytically answer whether there's a kink at t equals 0 or if it's smooth.
Oh, yeah. It's it really comes out at an angle, if that's kind of what you're asking.
Yeah. Okay. Great.
I have another question. I don't know, maybe, yeah, if I'm allowed, maybe there are other people that want.
If the
Okay.
speaker doesn't complain, you're allowed.
Okay.
When Kristan has to go, he just has to say.
Okay. Yeah, that's the advantage of starting early in the morning. So maybe you mentioned, and I've missed, you chose a kinetic term, a time derivative with a single time derivative. Was it
Yes.
crucial, or one can consider time derivative terms? And if so, is there an effect in the discussion of having relevant or irrelevant operators because you are playing with higher derivatives and so?
Yeah. So, I mean, at some level, one should be able to do effective field theory modulo the subtleties that I've mentioned, where you do have to pay attention to lattice sensitivity. Right. So why did I do one-time derivative in the model that I presented? The reason why was merely technical convenience. What happens with one-time derivative is that the Dyson equations are just much simpler to solve. That's the reason. With Amir, we have a project that we're writing up now where we study the models with two-time derivatives. And what happens in those models is, what's the way of saying it? You can ask in everything that I wrote above, what is going on with renormalization? That's kind of what you're asking at some level. And
indeed.
what happens is that in the one-time derivative models, those are really more like many-body quantum mechanics with, in this case, 2-to-2 interactions. They're much softer in the UV than things with two-time derivatives. And so we had various ways of renormalizing our Dyson equations. We had like a dim-reg, we have like a polyvolars, we have a lattice one even that I didn't discuss. We have all these different methods of renormalizing. They all get the same answer, and so we're very confident in what we're doing. That was the story back in May. The two-time derivative models, well, now you really have to work a bit harder. So for instance, what we found when studying the two-time derivative models is that dim-reg, if you can dimensionally regularize these models, but the dim-reg, well, the basic question you have whenever you regulate anything is, does it preserve the symmetries that you're wanting to maintain? That's the basic question. And in gauge theories, we've known the answer since forever. In this context, dim-reg actually breaks the dipole symmetry. There's some other things that you have to pay attention to. So these quartic kinetic terms, to get a finite theory, those have to be those couplings, this is the answer, they have to be multiplicatively renormalized. And it's easiest to kind of do, we understand now what we're doing, long story short, with the renormalization, and things are organized by energy scale when we do that. It's just the one-time derivative models, they're much simpler, and you don't have to deal with as much of this.
Okay.
I hesitate to go further because it gets technical.
Okay, yeah.
Good. we've had a lot of questions. I think we'll thank Kristan here. Thanks a lot for answering all the questions.
Hopefully this was useful. Thank you very much for the opportunity.
No, thank you. Also for the waking up so early. So let me stop there. And see you all, I think it's in 2 or 3 weeks. We're still getting some extra talks.